is a graph composed of multiple nodes and multiple connected edges. Each edge has a weight which represents the length of this edge. If we want to start from 0 and arrive at 4, so what should be the shortest path? What is the shortest path length? Today we will talk about the Dijkstra algorithm. First, we need a table to record the distance from node 0 to all nodes. Both are infinite at the beginning. In addition, in order to record the shortest path, it is necessary to record the nodes before each node in the shortest path, which are now empty. First of all, the distance between node 0 and itself must be 0. Then check the node with the shortest distance among all the nodes. Of course, it is 0 itself. Mark 0 as the node in the optimal path. Next, update the distance of node 1 and node 7 adjacent to node 0 to be 4 and 8 respectively. Therefore, in the table on the right, you can update the starting point 0 to node 1 and node 7 to 4 and 8, and node 0 as the previous node of node 1 and node 7. Then we look for the node with the smallest distance from the starting point among the unlabeled nodes. That is node 1. Mark it and include it in the optimal path nodes. Try to update the neighboring nodes of the newly marked node 1, which are node 2 and node 7 respectively. First, the edge length from node 1 to node 2 is 8. If the optimal path from 0 to 2 passes through node 1, the distance is 12, which is less than infinity, and the distance of node 2 is updated. The node ahead of node 2 is node 1. Then let's look at node 7. If starting point 0 passes through node 1 to node 7, the distance is 15. However, this path is greater than the original distance of node 7. Therefore, it is not updated. Then we look for the node with the smallest distance among the unlabeled nodes, which is node 7. Mark it and include it in the optimal path. Next, try to update the neighboring nodes, node 8 and node 6 respectively. From the starting point 0 through node 7, the distance to node 8 is 15, and the distance to node 6 is 9. They are all larger than infinity. Update the distance and set their previous node to be node 7. By analogy, we can summarize what we did just now into two steps. First, each time the node closest to the starting point is selected from the unmarked nodes, marked and included in the optimal path set. Second, calculate the distance of the neighboring node B that just joined the node A, excluding the marked node. If the sum of the distance of node A and the length of the edge from node A to node B is less than the original distance of node B, the distance of node B and the previous node are updated. It loops in this way until the destination is marked. That is, the shortest path from the starting point to the destination is found. According to this rule, the shortest distance in the unmarked search is node 6, and marked and included in the optimal path. Try to update node 8 and node 5 adjacent to node 6. The distance from the starting point to node 6 is 9. If it passes 6 to 5, then the distance to node 5 is 11. Update infinity, and the previous node is node 6. From the starting point, the distance from node 6 to node 8 is 15, which is the same as before, so it will not be updated. Let's speed up our pace. Next, look for the node with the shortest distance in the unlabeled nodes, which is node 5. There are 3 neighboring nodes. If you pass through node 5 and reach these 3 nodes, then the distances are 15, 25, and 21 respectively. Node 3 and Node 4 are updated. Node 2 is not updated. Next, the shortest node in the unmarked is Node 2. Its neighboring nodes are Node 8 and Node 3. Node 5 is not needed because it already marked. If you pass through Node 2 and reach Node 3, then the distance is 19. Update the original 25, and the previous node will also be changed to Node 2. If you pass through Node 2 and reach Node 8, the distance becomes 14. Update. Then the node with the shortest distance is Node 8. Neighboring nodes are already marked and do not need to be updated. Then, the shortest is Node 3. Attempt to update the unmarked neighboring Node 4. If it passes through Node 3, the distance of Node 4 is 28, which is greater than 21, so it will not be updated. Finally, the destination Node 4 is marked. Update completed. Finally, the shortest distance from the starting point 0 to the destination Node 4 is 21. So, how is the shortest path? We follow the previous points and go back in reverse. First, Node 4 is in front of Node 5, then 6, then 7, and finally the starting point 0 is reached. Then, this path is the shortest path. The Dijkstra algorithm is the shortest path algorithm from one vertex to the other vertices. The node edges have their own different weights, but they all must be positive numbers. If they are negative numbers, bare-manifold algorithm is needed. If you want to require the shortest path between any 2 points, you need to use the Floyd algorithm.